Hi, I'm Trevor.
And I'm Dylan.
And this is our ME102B project, which is a pyro valve. So pyro valves are used widely in the aerospace industry because they're reliable and they're relatively simple. So for our project, we wanted to make a pyro valve, and we also wanted to make it smaller than they usually are. So you can see this is a very small part. It's about 4 millimeters in diameter. And this was our motivation for the project, making it small, making it reliable, and in essence, making an actuator for this project. So you can see how these valves work is when they're in the closed position, these are O-rings right here, which do not allow fluid flow past them. So the inlet cannot flow through, but when the igniter explodes, which generates gases to push the valve open, you can see fluid can flow from the inlet to the outlet right here, and fluid can flow through. Now, one interesting or challenging part of this design to highlight is needing it to seal. So the igniter in here must reach high pressures in order to push the valve open, which means that you need to have a good seal. That seal is accomplished by having epoxy at the end of the igniter on this side and having O-ring seals and PTFE tape on this side, which you'll see in the next video. So you can see the igniter slides in. Getting this to seal was a major challenge of the project. It took around 12 attempts of different 3D printing charges and different designs like these to get it to seal properly. But yeah, you'll get to see it working in the next video.
Go.
So here's the integrated system for testing. You can see the valve body is right here. The piston, as shown earlier, is inside this valve body and moves back and forth. This green printed part right here is the charge holder. You can see the wires from the charge that come out the back of this. These are attached to the relay right here, which allows you to actually control the firing of the charge. Up here, there's this fitting that basically connects the valve body to this little funnel that we have that holds water. And this funnel is connected to the load cell here so that we can measure how much water is in the whole assembly.
So now moving on to demonstrate the state machine. The state machine initially begins with a calibration state that does not require user input besides launching the actual code. This is meant to take 100 readings, which is then averages to account for all the default weight on the load cell that is not the added fluid. As you can see, it initially takes 100 readings, and once it takes these readings, all future measurements are taken with respect to the set point. And as you can see, the magnitude of the readings do drop significantly after the calibration is completed. Onto the circuit, we have an LED that signifies the active firing state when it is allowed to fire. When it is off, it cannot fire no matter, even if you press the actuation button. Then we have two digital buttons. The closest one actually initializes a safety state, and this actually fires the pyro valve if it's in an active configuration. If we push on it, you can see it and apply load, it does become active fire, but if you move it, it turns off for safety. Also, if we add fluid to symbolize a propellant in a monopropellant system, the state is on. If we put the safety on, light goes off, and we cannot fire the valve. And as you can see, the valve is not leaking, it is closed. If we take the safety off, and then push the button to actually actuate the valve,
and you could see a bit of sparks come out the right side there, and now you can see pretty clearly that there's water dripping out of the valve. This does drip pretty slowly, but it'll drain the rest of the fluid here, and the piston has successfully moved inside.